Carbon dioxide could one day be captured from the air and turned into useful products such as plastics, paint and explosives thanks to a new invention from scientists. The compound, which is the #1 driver of climate change, could be converted into methanol using a newly discovered metal catalyst. The catalyst could be used to speed up the conversion of carbon dioxide into methanol, one day making it a cheap and easy process, the researcher said. Methanol is poisonous to humans and may cause blindness, coma, and death if ingested. But handled carefully, the chemical can be used to make a range of useful products including plastics, paint and explosives. Catalysts speed up chemical reactions by bringing together reactants in a way that makes it easier for them to break and rearrange the bonds holding them together. But for a catalyst to be useful, its active site, the site that interacts with chemicals to speed up reactions, must be known. Researchers from the U.S. Department of Energy's Brookhaven National Laboratory tried to uncover the active site of the catalyst that helps turn CO2 to methanol. This catalyst, made of copper, zinc oxide, and aluminum oxide, is used in industry, but it's not very efficient or selective, said Brookhaven chemist Dr. Ping Lu, the study's lead author. We want to improve it and get it to operate at lower temperatures and lower pressures, which would save energy, she said. Prior to the study, different groups of scientists had proposed two different active sites for the catalyst. Scientists had decided that the active site of the metal catalyst was either a portion of the system with just copper and zinc or a portion with copper and zinc oxide. We wanted to know which part of the molecular structure binds and breaks and makes bonds to convert reactants to product, and how it does that, said Dr. Jose Rodriguez, a Brookhaven chemist. To find out, the researchers performed a series of experiments using well-defined model catalysts, including one made of zinc nanoparticles supported on a copper surface and another with zinc oxide nanoparticles on copper. To tell the two apart, he used an X-ray beam to zap the samples and measured the properties of electrons emitted. These electronic signatures contain information about the oxidation state of the atoms the electrons came from. This helps researchers work out whether the copper surface was covered in zinc or zinc oxide. They also used computer modeling to predict how these two metal catalysts would play a role in the conversion of CO2 to methanol. These theoretical studies use calculations that take into account the basic principles of breaking and making chemical bonds. The factors analyzed in the computer modeling include the energy required for the reaction, the electronic states of the atoms, and the reaction conditions. This allows scientists to derive the reaction rates and determine which catalyst will give the best rate of conversion. We found that copper-zinc oxide should give the best results, and that copper-zinc is not even stable under reaction conditions, said Lu. In fact, it reacts with oxygen and transforms to copper-zinc oxide. Those predictions matched what the team had observed in the laboratory. We found that all the sites participating in these reactions were copper-zinc oxide, he said. In our simulations, all the reaction intermediates, the chemicals that form on the pathway from CO2 to methanol, bind at both the copper and zinc oxide. Dr. Shyam Kettle, a chemist at the laboratory, said. So there's a synergy between the copper and zinc oxide that accelerates the chemical transformation. You need both the copper and the zinc oxide. Designing a new catalyst that optimizes the copper-zinc interface will be key for designing a catalyst capable of quickly turning carbon dioxide into methanol, the scientist said.